Quantum computing has everyone terrified of the implications it has on cybersecurity. It's simply too powerful. But what if there's a way to not make computers more powerful, just faster, without the risk of having hackers constantly bugging you? Meet optical computing. The way regular computers work is by transistors communicating via electricity, or in particle terms, sending electrons to one another. However, communicating with light by virtue of the particle of light, photons, is actually far easier. We already do it through fiber optic networks and other things, so the concept of optical computing is actually not as far-fetched as you might think. The basic idea is that instead of electricity traveling in between transistors and circuit boards, you have photons doing the exact same thing. But why does this make computers faster? One of the answers lies in processor lithography. Lithography, with regards to CPUs, refers to the size of the transistors on the CPU. More transistors equals more performance, so smaller lithography results in a better CPU, since if you have a smaller transistor, you can fit more of them on the CPU. The thing is, photon-powered computing allows for much smaller transistors, meaning the performance ceiling is much higher. A given electron in a semiconductor of electricity, such as silicon, will get excited when hit with the photon with greater energy than itself. This makes the electrons let out photons of their own, which creates a light wave. The way energy is preserved is using total internal reflection. So that anytime light reflects off of a surface, it creates an angle of reflection and an angle of incidence, and by the law of reflection, these angles are always equal. For each reflection, there's a critical angle, and if the angle of incidence is at that or greater, it'll always reflect and not refract, which is called total internal reflection. This ensures that a light wave stays inside a cable. A regular transistor has two states, on or off. An optical transistor would need this too, and the way people are theorizing this will look is with polarization. This can effectively keep a light ray on or turn it off. Imagine a rope shaking vertically up and down like a wave and a fence. That fence would only allow the rope through it if the fence's sticks, were perfectly parallel to the way that the rope is shaking. That's how polarization can turn a light ray on or off. If the polarizing filter is parallel to the light wave, it'll let it through. If not, it'll block it or turn it off. Now that you have an understanding of how optical computing works, let's talk about its benefits. The thing is, with regular computing, a copper wire can only be used to transmit one channel of information at a time. However, with optical computing, this is not the case because different photons with different wavelengths can't interact with one another. This way, several light waves may propagate through a single channel for a more efficient transmission. Another benefit of optical computing is that a photon-based transistor can be reused much faster than a regular one can, meaning signals can be stored and registered faster, resulting in a speedier computer. We mentioned earlier that optical computing can achieve a smaller transistor size, another performance benefit, but how does this work? The answer is quantum tunneling. Quantum tunneling is the effect that takes place when an electron is too small for the transistor. The electron can't go through the transistor, it'll just pass through it as if it wasn't there. It's a large topic on its own, and we can't go too in-depth about it in this video, but the gist of it is that once the transistor gets too small, the electron skips past it as if it wasn't there. Since this doesn't happen with photons, optical computing can achieve a much smaller potential transistor. We'll pay for any damage we did to your brain. Just let us know with a like.